Hi, my name is Scott Horton, and I'm part of Group A for the Nuclear Energy Engineering Technology Capstone class that began in March at Thomas Edison. My group is myself and Jerry Hiley and Nate Coy, and this is part one of our oral presentation on nuclear renaissance entitled The Future of Nuclear Power Generation in the United States, Revival or Demise. Nuclear renaissance is a term that was coined around 2001 referring to the perceived revival of the nuclear power industry. This revival was driven by economics based largely on the increasing fossil fuel prices and also over concern over the environment and being able to comply with greenhouse gas emission limits. In part one of this discussion, I will talk about the current state of affairs in the nuclear power industry in the United States, including construction at V.C. Summer, also the closing of the Kewaunee Nuclear Station, as well as the impact the Fukushima event has had on nuclear generation in the United States. I'll also discuss two types of reactor designs and their feasibility in the United States, and that's the advanced boiling water reactor design and the pebble bed modular reactor design. Growth is occurring in the nuclear industry in the United States. 20 miles northwest of Columbia in Jenkinsville, South Carolina, the South Carolina Electric and Gas Corporation has begun construction on two AP1000 plants at the V.C. Summer site. South Carolina Electric and Gas applied for the combined operating construction license in March of 2008 and was granted approval in March of 2012. Construction began on Unit 2 with the first concrete pour in March of 2013. This was the first construction on a nuclear power plant in the United States in 30 years. In October of 2014, the project suffered a significant setback due to fabrication delays based mostly on the modular design of the reactor building itself. Construction is progressing, with Unit 2 expected to complete in late 2018 or early 2019, and Unit 3 expected to complete approximately a year later. These AP1000 plants are approximately 1,100 megawatt units, and the AP1000 design was chosen because it has fewer moving parts, it has safety systems that rely on gravity instead of power supplies and motor-driven components, and it has a 60-year design life. These plants have 85% less cable, 80% less piping, 50% fewer valves, and 35% fewer pumps than the average existing nuclear plant. They also require about 45% fewer seismic 1 rated buildings. We have also been experiencing a loss of megawatt generation in the United States. Perhaps the most notable is the Kewaunee Power Station closing. Kewaunee was located in Carlton, Wisconsin, which is about 27 miles southeast of Green Bay. What makes the Kewaunee closing significant is at the time of its closing, Kewaunee was a top performing plant. In fact, in 2010, Kewaunee won the American Nuclear Society Utility Achievement Award for outstanding performance in plant operations and received an INPO 1 that same year. Dominion purchased Kewaunee in 2005 with the intention of it being the first step of them establishing a nuclear fleet in the Midwest. They purchased it from Wisconsin Public Service and from Alliant Energy. In 2008, with the onset of the recession and with increased production, shale production in the United States, natural gas prices began to drop. Kewaunee was operating in an open market environment and simply wasn't able to compete with the natural gas prices. In 2012, when the previous owners, Wisconsin Public Service and Alliant Energy, when their contracts to buy energy from Kewaunee expired, they elected not to re-up their contract. This was pretty much the nail in the coffin for the Kewaunee station. And in October of 2012, Dominion announced that they would be closing the plant. Kewaunee came offline permanently in May of 2013. Currently, Kewaunee is scheduled to have all of their fuel loaded into dry cask storage by the end of 2016. At that time, they will enter what is called a Safe Store program, where they will be monitored for up to 60 years. And at the end of that time, that will allow some time for radioactive decay, so that when the final decontamination occurs, there will be less radioactive waste to dispose of. Currently, Kewaunee is scheduled for final decommissioning and dismantlement in 2069, with the site being available for unrestricted use in 2073. Excuse me. On March 11, 2011, a 9.0 earthquake off the coast of Japan triggered a massive and very destructive tsunami. This tragedy accumulated 15,891 confirmed deaths, with 2,500 people still missing. 4 years later, an estimated 230,000 people are still living in temporary housing due to their homes being destroyed or the areas they lived in being uninhabitable. The impacts of this event are far-reaching, but the impact we want to discuss today is how it affected our nuclear renaissance. The nuclear plant at Fukushima Daiichi houses 6 boiling water reactors. At the time of the event, Unit 4 was defueled. Unit 5 and Unit 6 were both in cold shutdown for planned maintenance. Units 1, 2, and 3 were operating normally. Excuse me. Following the earthquake, plants 1, 2, and 3 shut down automatically as designed. The emergency generators started automatically as designed, and the plant was safe and stable. The destruction really started 50 minutes later when the tsunami arrived. The tsunami was estimated at 46 feet tall, the wave that hit the plant. The seawall around Fukushima Daiichi was approximately 33 feet tall. When the tsunami breached the seawall, flooding occurred at the Fukushima Daiichi plant, which flooded the emergency diesel generators and resulted in a complete loss of power. With no power available, cooling was not able to be restored to the reactors, and temperatures began to increase to the point of meltdown. At the excessive temperatures, a Zerk water reaction occurred, creating massive amounts of hydrogen buildup, and explosions resulted at units 1, 2, and 3. The fallout from the Fukushima event around the globe has been varied, and that's really an understatement. In the U.S., however, public opinion of the future of nuclear power has changed very little. As a matter of fact, in March of 2011, just prior to the Fukushima event, a Gallup poll was conducted, and 57% of Americans approved of extending licensing for existing operating plants that were within federal regulations, and for the addition of new nuclear power plants in the United States. 1 year later, following Fukushima, the same poll was conducted, and the numbers were almost identical, with again 57% showing approval of seeking new nuclear power generation in the United States. Even with public opinion still seemingly favoring nuclear power, the ramifications of the Fukushima event are being felt in the nuclear industry in the United States. In March of 2012, the NRC issued 3 orders for the U.S. nuclear generation fleet. The first order entails the addition of equipment at all existing plants to help respond to an extended loss of electrical power and the loss of the ultimate heat sink, and to maintain cooling and maintain the containment integrity. The second order is for improved spent fuel pool level and temperature monitoring. And the third order deals specifically with the 33 operating boiling water reactors in the United States, requiring them to install reliable, hardened containment vents which would operate under any circumstance. For the existing plants, a plant survey was conducted in 2013 of all the utilities in the United States that are currently operating nuclear power plants. This survey estimated that over the next 3 to 5 years, to bring all 102 operating plants up to regulations, to meet the regulations the NRC put out, it's estimated it's going to cost approximately $3.6 billion. The impact on the new plants that are being constructed has been very minimal, largely due to the fact that their safety systems are passive, meaning that they don't require electricity or motor-driven pumps to initiate the safety systems. They're all gravity fed. For Watts Bar 2, who already has their construction license but not an operating license, they have to be in compliance before the NRC will issue them their operating license. For the other 4 plants, the 2 at VC Summer and the 2 at Vogel, who already have a construction and operating license, they have to be in compliance prior to their initial fuel load. There are other types of reactor designs that are being researched for possible development in the United States. One of these designs is the Advanced Boiling Water Reactor. In 1997, the NRC approved the GE Nuclear Energy single-cycle, 4-circulation Advanced Boiling Water Reactor design. In September of 2007, the South Texas project applied for a license to build 2 Toshiba Advanced Boiling Water Reactor at their facility at South Texas project. In October of 2009, Toshiba informed the owners group that the cost was going to be closer to $14 billion instead of the $10 billion that they originally projected. One of the owners, City Public Services of San Antonio, who was a 50% shareholder at the time, reduced their stake from 50% to 7.625%. And in April of 2011, the owners group decided to stop pursuing the permitting process, citing at the time the ongoing expense of the planning process and the slow process of the permit itself. So that project is no longer in the works. There are 4 operational advanced boiling water reactors that we have been able to obtain some operating experience from. Some of the more significant improvements they have discussed is the reactor internal pump. The reactor coolant pumps are actually mounted on the side of the reactor vessel. This has several advantages, one being you don't have the massive amounts of primary coolant piping, which leads to a smaller plant size. You also have fewer in-service inspections required because you have fewer welds. Another advantage deals with the emergency core cooling systems. With the advent of the reactor internal pump and the internal circulation and the lack of all the primary coolant piping, you have a decreased chance of a piping break causing a loss of coolant accident. This gives you a lower core damage frequency calculation. Another major advantage for the advanced boiling water reactor design is the reactor pressure vessel itself is made of forged rings instead of the welded plates that we've used in the past. This leads to a sturdier reactor pressure vessel, a longer life expectancy. These vessels are projected to have a 60-year life expectancy. They have 30% fewer welds, which again leads to fewer in-service inspections required, less maintenance cost. There are none currently planned in the United States, but with the NRC already approving this reactor design, there is the possibility, and it is feasible, for this type of plant to be built in the United States in the future. Another technology that really gained momentum in the 2000 to 2005 time frame is the pebble bed modular reactor design. This is actually a very old design dating back to the 1960s that really, with some of the newer technologies, has gained momentum again. It's a graphite moderated gas cooled reactor. The basic design is spherical fuel elements called pebbles. They're about the size, a little bit smaller than a tennis ball. This pebble includes the fuel, which could be uranium or thorium or plutonium or even a MOX fuel, the moderator, the graphite itself, and the fuel barrier, all in the same unit. Excuse me, not the fuel barrier, the fission product barrier, all in one unit. Each pebble cycles from the bottom to the top of the reactor 10 times over the course of approximately 3 years. Each time it comes out of the core, it is tested, and if it meets acceptance criteria, it's routed back into the core. If it doesn't meet the acceptance criteria, if it is depleted and at the end of its life, that pebble is removed from circulation and a new pebble is inserted. The heat generated in the core itself is cooled by an inert gas, normally helium, and then that gas is directly transported to the turbine. In the event that a different gas is used, like carbon dioxide or some other gases that could become radiated by neutron absorption, the gas could be sent to a heat exchanger to heat another medium, or to a steam generator to produce steam to drive the turbine. There's very little operating experience with these pebble bed modular reactors. The only operating pebble bed modular reactor currently is a small 10 megawatt unit at the Tsinghua University in China. This reactor went critical in 2000 and connected to the power grid in 2003. The success of this plant has led to China breaking ground on a demo project that happened in July of 2013. This project is a 200 megawatt plant and features 2 modular reactors feeding 1 turbine. The 2 reactors are rated for 100 megawatts apiece, and the turbine, the single turbine, is rated for 200 megawatts. The expectation with this plant from the Chinese government is that it will begin generating commercial electricity in 2017. Due to the fact that we have such little operating experience on the pebble bed modular reactor design, many of the advantages and disadvantages cited by critics and opponents is theoretical at best. Some of the advantages is that the reactor is inherently safe due to the high operating temperatures. These reactors, like most reactors, have a negative temperature coefficient of reactivity. Therefore, as temperature goes up, it drives power down. There are a wide range of fuels that could be used in the same basic reactor design. I discussed earlier, uranium, thorium, plutonium, and even MOX fuel could be used in this design. The fuel replacement is continuous. This gets rid of the need for long extended outages to replace the reactor fuel. And this reactor design is cooled by inert gases, which limits or eliminates the possibility of a steam explosion that we see in the light water reactor designs. Theoretically, they say that all support systems for the pebble bed modular reactor design could fail and the reactor would survive. It would increase to a designated idle temperature, and it would stay there indefinitely, allowing for the fuel to either be removed or maintenance to be performed on whatever the systems were that failed. The disadvantages with this type of reactor is that the graphite material itself is combustible. So if there were a fire, the fuel could be carried away in smoke. And this is further compounded by another disadvantage in that the graphite pebbles rub together, and that friction creates pebble dust, graphite dust, and that dust could become airborne as well in the event of a fire or external attack. Another disadvantage of this type of reactor is that the volume of radioactive waste, due to the amount of pellets, each of these reactors over the course of its life would go through approximately 360,000 pebbles. So the sheer volume of radioactive waste would be increased. There was a small German project called AVR that was a pebble bed reactor design. This project operated for about 21 years with a lifetime capacity factor of approximately 70%. It was shut down in 1986, shortly after the Chernobyl accident. There has been one large-scale attempt at a high-temperature gas reactor. It was located at Fort St. Vrain in Colorado, and it was considered a massive failure. This plant operated between 1979 and 1989. It had a forced outage rate greater than 60%, and it had a lifetime capacity factor of 14.5%. By comparison, baseload plants today are designed with a capacity factor of greater than 75%. No pebble bed designs have been approved by the NRC, and currently I would say the feasibility for this type of reactor in the United States is very low. However, with the project going on in China, if that project were successful, it is possible that in the future some of those designs could be incorporated and could make this type of reactor feasible for the United States. This concludes part one of our presentation. Jerry Hiley will be conducting the second part of our presentation. Thank you.